Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. In our introduction video to optimization, we looked at basic problems like fencing setups and open boxes. But exam boards don't want you to just optimize simple geometry. They want to see if you can find the shortest distance from a point to a parabola, or maximize the volume of an inscribed cylinder where the constraints are completely hidden. Today, we're going to take on two elite exam-style problems. The first one is a classic AP Calculus distance minimization puzzle, and the second one is an IB Math HL inscribed geometry challenge. Now, before we jump in, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. For our first problem, we want to find the point on the curve y is equal to the square root of x that is closest to the point 3, 0. Now we know that the distance between 2 points is d is equal to the square root of x minus x1 squared plus y minus y1 squared, where xy is 1 point and x1, y1 is the other point. Now, as you can see, this is quite a messy formula. If we want to minimize this, when we take the derivative, we're going to have to deal with chain rule and a bunch of things. So the trick here is that to minimize this, this is the same as minimizing the square of the distance formula. So meaning it's the same as minimizing d squared. And by doing it this way, we can get rid of the square root. So then what this means is that our objective equation is going to be d squared, which is x minus x1 squared plus y minus y1 squared. And then our constraint is going to be the fact that our curve is y is equal to the square root of x. So now what we're going to do is we're going to substitute y is equal to the square root of x into our objective equation. And then we're just going to rename our objective equation as a function of x, so f of x, and that is going to be equal to x minus, and here our x1, y1 would be the coordinate of that point, which is 3, 0. So this would be x minus 3 squared plus square root of x minus 0 squared. And then just expanding and simplifying this is going to give us x squared minus 6x plus 9 plus x, which simplifies to x squared minus 5x plus 9. So now we can go ahead and take the derivative so that we can find our critical points, which means we get f prime of x is equal to 2x minus 5, and then we're going to go ahead and set it to 0. So we get 0 is equal to 2x minus 5, which means our critical point here is x is equal to 5 over 2. And we know for a fact that this is a minimum because f prime of x is an increasing function. So what that means is if we draw a number line and then we plot our critical point at 5 over 2, f prime of x is going to be negative before 5 over 2, and then it'll be positive after 5 over 2. Which means our function would have been decreasing before that and then increasing afterwards, so therefore we have a minimum. So now finally, to answer the question, we want to find the point on the curve, which means we need a full coordinate pair. So using x is equal to 5 over 2, we can go ahead and find our y value, and y is going to be equal to the square root of 5 over 2, and then we can also go ahead and rationalize this if we wish. So multiplying this by root 2 over root 2 is going to give us root 10 over 2. So therefore, our answer here is going to be the point 5 over 2, comma, root 10 over 2 is the closest point on the curve. Now for our second question, we have a right circular cylinder that is inscribed inside a sphere of fixed radius capital R. And we want to find the maximum possible volume of the cylinder in terms of capital R. So I'm just going to go ahead and draw a diagram to illustrate what that looks like. So let's say this is our sphere. One possible cylinder that we can have in there could look something like this, where we have, this is the inscribed right cylinder. So this one is, we can say maybe a little bit taller. But we could also have a cylinder that looks something like this, where it's much wider, but also much shorter. So the green one would be one possible cylinder that's inscribed in there, and then the red one would be another possible cylinder that is inscribed in the sphere. So the question is, what cylinder is going to give us the maximum possible volume? Now, first of all, this is a classic IB problem because it uses a constant parameter, capital R, instead of giving you a number, which makes the question just a little bit more complicated. But let's say our cylinder has a radius of lowercase r. What we want to do is we want to express this radius as well as the height of the cylinder in terms of the parameter capital R. So let's see how we can do that. The first thing that we're going to write down is our objective equation. So the objective equation is going to be the volume of a cylinder because that's what we're trying to maximize. So we get capital V is equal to pi times r squared h, where the lowercase r is the radius of the cylinder and the lowercase h is the height of the cylinder. Next, notice that if we have the center of the sphere here, going from the center of the sphere to this edge of the cylinder is the radius of the sphere. So that is our capital R. Doesn't matter what cylinder we have. So in the case of our green cylinder, it would be from the center to right over there. And again, that is capital R. So now we can see that we actually have a triangle here formed by capital R, which is the radius of the sphere, the lowercase r, which is the radius of the cylinder, and this distance here, which is half the height of the cylinder. So that means our constraint equation is going to be the equation that relates them together, which is lowercase r squared plus h over 2 squared is equal to capital R squared, because we have a right angle triangle in all those cases. So now from our constraint equation, we could either isolate lowercase r or we could isolate lowercase h. And you're going to get the same answer regardless of which direction you go. However, one of them is going to make your life a little bit easier than the other. And the reason is because if we look at our objective equation, we can see that we have an r squared and we have an h. So if we want to isolate h, notice how from this equation to isolate h, we're going to need to end up square rooting the other side so that we can isolate h. Whereas if we were to isolate r, we can actually just isolate r squared because within our objective equation, it is already r squared. So that means we're going to go ahead and isolate r squared. So we get lowercase r squared is equal to capital R squared minus h squared over 4. Next, we're going to take this and we're going to substitute it into our objective equation. So now our objective equation is going to be only in terms of one variable, which is lowercase h. And the reason is because capital R here is a constant and not a variable. So we get V of h is equal to pi times capital R squared minus h squared over 4 times h. And we're just going to go ahead and expand that, and that becomes pi times capital R squared times h minus pi over 4 times h cubed. And now we're ready to go ahead and find our critical point, which means we're going to take the derivative of v of h. So we get v prime of h is equal to pi times capital R squared minus 3 pi over 4 times h squared. Setting v prime of h equaling to 0, and then solving for h is going to give us our critical points. So let's go ahead and isolate h. So we get 3 pi over 4h squared is equal to pi times capital R squared. Cancel out the pi on each side, and we get h squared is equal to 4 capital R squared over 3. And then we're just going to take the positive square root of both sides, and we get h is equal to 2 times capital R over the square root of 3. And then we're just going to go ahead and do a quick check to make sure that this is in fact a maximum. And this time we're going to do the second derivative test. So we get v double prime of h is equal to 0 minus 3 pi over 2 times h. And now we're going to go ahead and substitute in our critical value of 2 times capital R over root 3. And we can see that since capital R is a positive constant, once we substitute this number in, we get this as a negative number. So we get this as less than 0, which means our graph is concave down at that point. So because it's concave down, that means our critical point here is a maximum. So now finally, to answer the question, it was asking us for the maximum possible volume of the cylinder. So which means we need to now go ahead and substitute this h value back into our volume equation. Before we do that, we need to find what r squared is. So first thing we're going to do is take this value for h and substitute it in here to find r squared. And that gives us lowercase r squared is equal to capital R squared minus 1 over 4 times 2 times capital R over root 3 squared. And this is equal to capital R squared minus 1 over 3 times capital R squared, which is 2 over 3 times capital R squared. And now we can go ahead and find the volume, and we get v is equal to pi times lowercase r squared, which is 2 over 3 times capital R squared, times h, which is 2 times capital R over square root 3, which gives us a final volume of 4 pi over 3 root 3 times capital R cubed. And this is the maximum possible volume of the inscribed cylinder. And now let's do a quick recap of what we covered in this video. We learned the function squared trick, which is when minimizing a distance, we can optimize the function d squared rather than d to avoid working with messy square root derivatives. We learned to treat constants as numbers. So like we saw in the second example, that capital R was a parameter and not a variable, because it was something that stayed constant. So therefore, we treat it like an ordinary number when taking derivatives. And again, always make sure you do your domain sanity check to ensure that your critical point makes physical sense within the boundaries of the geometric constraints. And now it is your turn to give this a try. Can you find the solution to the problem on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.